All right. Let's continue with our last example from Tuesday, which is a swap program. I want to use that example to show you in detail how you're supposed to prove if a given program is correct. Let's make sure you follow the right formats, so you're gonna get it right on the exam. Okay. Again, so these are the rules that we have talked about so far. Let me just go over them very quickly as a review, quickly. Okay. We have seen them all already from Tuesday. So far we talked about how we can calculate the weakest precondition. So that's step number one you should do. Calculate the WP, and whatever WP you get, you want to make sure the actual precondition for your program implies the WP, right? No weaker than that. You got WP over here, WP over here, WP over here. But we got different cases. Case number one, the simplest one, you simply got a simple assignments. In which case, you simply take the postcondition and replace every occurrence of X, the targets of the assignments, by the source of the assignments. So we'll see examples in just a moment. Right, that's the simplest one. And then it could be a little bit more complicated over here when you have an alternation over here, which can be if then else, or if, else if, as many else if as you like, as we show. WP stands for what, guys? Thank you, weakest precondition, okay? Okay. Now, and then you say that is equal to, so you got two branches. Either the branch condition over here, B, is true, or it is not true, right? Either case. And then you want to say if it is true, then we can take that as an assumption. So that's why we got an implication over here. Under the assumption that we are executing branch number one, which means B is true, we can calculate the WP, and then S1, which is the action for branch number one. And then that should really establish the postcondition R. And similarly, we say S2, which is the action for branch number two, should also establish the same postcondition. And most importantly, we did spend quite a bit of time last time. It should be a conjunction over here, right? Rather than disjunction. Okay, keep that in mind. In case you forget, you can reproduce the example we talked about last time. Finally, this is slightly more complicated, which means if we have a sequential composition, simply means we got some execution over here followed by another execution. Okay, again, this is how you can think of it. We got S1 over here, we got S2 over here, and S1 started with some states. And after S1, we got some intermediate states. So the ending states for S1 is exactly the starting state for S2, right? That's the intermediate states. And after S2, we also got another ending state. We got three states to worry about. Okay? So now, the final state over here we want to establish is simply just the postcondition, which is R. Okay? So now we have to know under what circumstances can we guarantee executing S1 followed by S2 is going to establish R. That's the WP is about. Okay? So now, the intuition is we simply, let's say we ignore S1 just for now. Okay? Let's only consider S2. If S2 was the only execution to do in order to establish the R, what would that be? It would be simply the WP for S2 to establish R. That's what we know. So that's exactly the starting states for S2, such that we will establish R. But now we want to make sure, in order for S1 to really execute before S2, we want to make sure upon the termination of S1, we can also establish this. So it's as if you can think about the, let me highlight it over here. You can think about this WP is as if the postcondition of S1. That means in order for S1 to establish this intermediate postcondition, what should that be? Well, you just get a WP over here for S1 to establish something over here, and that one is exactly what the WP over here is, right? You will say WP for S2 to establish R. Okay, that's why you got that kind of two WP over there. Okay, simply because you got to execute one followed by the other. Okay. Realistically, you may not have just two statements. You may have more than two. Okay, but we're going to see that today all together in the beginning. Any question about the rules over here, the three? We are basically learning about under different scenarios how you can calculate the WP. There's one more to learn. We also have to learn about how to calculate the correctness for loops, but we'll talk about it after one example. Yes? Final exam, let me talk about the exam next Tuesday. Okay, guys, make sure you show up for the exam. No, not for the exam. Make sure you show, of course, you gotta show up for the exam. Make sure you show up on Tuesday. Okay? Well, I know you guys come anyway. Well, just make sure you come. Okay? Because no recording when I give tips for exam. All right. Make sure everybody comes. All right. Right. Let's see what we have. Okay, and then, so these are the proof rules that we also went over last time. Basically, the principle is, every time when you're given a whole triple over here, this is a predicate. How do you prove that this whole triple is true? You want to make sure whatever WP you calculate, so given some statements over here, which can be assignments, alternation, or sequential composition, and with some post-condition over here. You want to make sure the actual precondition is no weaker than that. Okay, it's at least equal or stronger than that. Right? That's what we keep emphasizing. Okay, and the proof rules we talked about last time. If you got doubts, please refer to the recording or talk to me. Are we ready to do one example all together? Okay, the swap. Okay. Okay, let's just go for this particular strategy. Your colleague also suggested another one. I would suggest you also try to prove it as well. But let's try this one here. This one is quite a standard one. Let's do it all together. The question is as simple as, is this particular whole triple correct or not? Okay? If it is correct, that simply means what? Okay? Let's think about the overall picture. So let's say the goal for us is to prove that the actual precondition, which is true, actually implies the WP for the program itself, which is for temp assigned to X, followed by X assigned to Y, followed by Y assigned to temp. So that's the implementation. At the end, we want to establish X larger than Y, right? The post condition. This is the goal. Agree? Okay? You don't really have to specify the goal in the exam answer. You don't have to. I'm just saying that's something you want to keep in mind. In order to establish this goal, we're going to split it into two steps. Step number one, we do the WP calculation. Step number two, whatever you calculate from step number one, which must be a predicate, we want to see if that one is implied by true. Okay? That's kind of the big picture. Let's do step number one. Usually step number one is the most difficult one, usually. Okay? Especially when you get loops involved. Okay, what I would do is, step number one, I want to calculate the WP. Okay? So now I'm just going to copy that again. So I would say start from here. So what's the WP for? Temp is assigned to X, followed by X is assigned to Y, and then Y is assigned to temp. And the post condition is X larger than Y. Okay? How do we do this calculation, right? If you look at that, it contains assignments. It also contains sequential composition, right? I would say typically you have to handle sequential composition first. Okay, so we got three phases. Okay, let me just highlight the three phases for you. I will show you how one way to break it down. Phase number one, phase number two, and phase number three. Okay, basically one way to think of it would be you can think about we want to make sure executing this is going to end up in a state that would be enough for these two to establish X larger than Y. That's one way to think of it. But, okay. And now, how do we go from there? One way how we can go from there is we simply say, okay, that would be. So now, let me just do a better highlighting for you. Let me just use blue to begin with. So now, let's say this, let's treat these two together to begin with. And we're going to split it up in just one moment. Okay? So what I would do is, I will first of all say, in order for this blue part to establish the post condition, I'm going to calculate the WP for that, right? So I'll simply write it down. I'll say that one would be just simply be the WP for X is assigned to Y, and then Y is assigned to temp, and then after which I'm going to establish X larger than Y. Okay, that's what I should establish, right? And now that shouldn't stand alone. We want to make sure after executing the very first phase, it's going to establish that. But what would be the weakest precondition for the first phase to establish the blue part as the post condition? For that, we have to apply the WP rule. So what I would do is I would say it's equal to by the WP rule for sequential composition. You can just put semicolon. It's understandable, okay, by us. So we can say it's going to be WP over here. For the first phase, temp is assigned to X. And then the post condition is going to be the blue part. Okay? That's by just one time of the WP rule for sequential composition. Any question for this, for the first time? First one. Okay, let's do something similar. So you can see, one thing to note, when we go from here to here, what we have gotten rid of is basically split up these two stages over here, right? That's something to note, okay? Okay, after this, let's do another one. Let me use another color. What about pink? So now what I would do is, now we got two stages over here. So we do something similar, okay? I'm going to just basically go backwards. So I would say, I will highlight the last stage over here. Everything except for the first stage, basically. And now, I'm going to say, in order for y is assigned to temp, to establish this particular post condition over here, what should be the requirements? Well, we calculate WP for that. And whatever that WP is, should be the post condition for X is assigned to Y to establish, right? Okay, let's do that first. So now for the pink part, it's going to be, I'll put WP over here. And then for Y is assigned to temp to establish X larger than Y. Okay, that's the pink part. And now let me go back here. And then we can see that in order for this to be moved out, we have to again apply the WP rule for sequential composition. I'll write it down first, and then I'll show you the result. We can say WP rule for sequential composition again. Okay, so what do? We simply just do the following. Okay, it's going to be blue. So I would say it's going to be, used to be the WP for X is assigned to Y. And now the post condition for this X is assigned to Y. It's going to be the pink, right? And then, so that's going to be something like that. And we can just copy whatever we have got before. WP, and then temp is assigned to X, is going to establish this part here. You can see the three colors over here, right? Let's just summarize what we have done so far. The pink part is going to be, we're kind of thinking backwards when we see that. The pink part is really the last stage that we're going to do. And the pink part is the WP in pink is guaranteed to establish X larger than Y after executing Y is assigned to temp. Okay, that's the pink part. And we want to make sure the blue one over here, X is assigned to Y to also establish this. But how can we guarantee that? We want to make sure temp is assigned to X is going to establish the WP for this to establish the pink part over here, right? Guys, any questions for this? It's a little bit fast, but let me know if you get lost. We're basically just applying the sequential composition rule for WP. Okay? I would suggest you do one after another. I wouldn't give you so many sequential compositions in the exam, but rather than if you somehow just do everything in one step, it's kind of risky. You might get something wrong. Okay? Any question about this before I move on? Yes? Yeah, eventually we want to prove that X is larger than Y, the pink one. Yes. Yeah. As you can see over here, that's the eventual post condition we want to prove, right? Yeah. We want to make sure, okay, we'll read it this way. What is the weakest precondition for the first stage to establish a particular post condition, which is, at the same time, the weakest precondition for the second stage to establish another post condition, which is at the same time the weakest precondition for the third stage to establish the final post condition. Okay, it sounds a little bit complicated, but it's not. Okay. Should I repeat again? Yes. Okay, I want to repeat one more time. Okay, I hope I am not making you bored. Okay, let's say this. Let's read it this way. We're asking the following question. What is the weakest precondition for this first stage to establish a particular post condition? And that post condition there is at the same time just also the weakest precondition for the second stage to establish another postcondition. And that postcondition there is also at the same time the weakest precondition for the third stage to establish the eventual postcondition we are requiring. Okay? Just understand this just for the very first time. Once you convince yourself, you don't have to think it in that way always. It's time consuming. Okay? Okay, so now what's left? So you can see now we have gotten rid of the sequential composition. There's no more sequential composition. And we don't have any alternation either. So what should we apply? What would be the WP rule? Assignments, right? If you tell me this is the answer, no, it's not the answer. You still got WP. I don't want to see in WP, right? So now, how do we apply that? Okay, so now in order to get rid of it, we can go from inner to outer. Okay, let me just undo this. Okay, let me handle the pink one first. Okay, the pink one is the only one I can do right now. Let's do the pink one. Okay, if I try to do the pink one, I will simply say is equal to, let's say, the WP for assignments. What would that be? That means I'm going to replace every free occurrence of y by temp in the predicates x larger than y. So what would that be? X greater than temp. Okay? That means I'll simply get x greater than temp. Okay? So that means I'll simply get something like this. So WP, just copy that. Used to be temp, it's assigned to x. That part hasn't been handled yet. And then the blue, WP, x is assigned to y. And now the pink part has been reduced to simply x greater than temp. Okay, you can see that specifically, I'm basically replacing this. Oh, that's not very good. Let me just use a different color. I'm basically replacing x larger than y and having x larger than temp because y has been replaced by temp, right? So what's so good? Okay, yes.
Isn't it supposed to be WP for assignment?
For x is assigned to y, yes. Oh yeah, of course. Thank you. You're absolutely right. Thank you. Okay, it's good to be 100% correct, absolutely. Okay, it's assignment. Okay, now what should we do? Well, now we can handle the blue part, right? For the blue part, what we can do is, over here, how can we simplify this guy over here, right? Again, we can apply the WP for assignments over here. Okay, so what would that be? Y is greater than temp, I agree, because x will be replaced by y. Okay, I'm writing it down. Okay, it's going to be WP for temp is assigned to x, and then we have the blue one, y is greater than temp. Okay, and now finally, okay, of course, by another final WP for assignments over here, what we will get eventually is something like this. Okay, so this is the final WP to simplify. Okay, replace every occurrence of temp by x. So that will simply be y greater than x. So that is the final precondition, weakest precondition. That's the answer. What's really amazing about the WP calculation is you can see that, let's see the big picture over here, right? What we gave in the beginning was a program. And at the same time, we also give another predicate, which is the postcondition we want to establish. What we get from this calculation is what is the weakest precondition for this program to establish the postcondition. Okay, now that is step one. Okay, but step two is going to be very straightforward. Okay, but of course we still have to verify that. And step number two, I'm going to put it here, right? Step number two, we are really asking ourselves the following question: is true implies y larger than x? Is that always the case? Yeah, exactly, right? Because but you thinking this way. The weakest precondition is very, very constraining about the relation between y and x. Y must be strictly larger than x. Okay? On the other hand, the existing precondition over here, true, is actually too tolerant. Okay? So I would say no. For example, let's say I'll give you some specific value. What about y is, let's say 1 and x is 2. So y is less than or equal to x. Okay, that's just one counter example. Okay, so you can see the only thing you want to be careful about step number 2. You don't want to really get wrong with the order of the implication, right? You want to make sure the existing precondition, in this case, it is true, implies the weakest precondition you just calculated, right? Guys, are we okay with this? Yeah.
Step 2, when we're trying to disprove something, it is enough
to give a counterexample. Yes, like what you learned in the logic course. You want to disprove a theorem, give a witness to prove the violation. Yes. So either you prove it or you actually give me one counterexample. I would say the one, what you are expected to do in the exam will be just slightly more complicated than this, just slightly. But that's pretty much what you can expect for this particular topic. Okay? If there's any question on that. Guys, any questions before I leave you with this? Yes.
I understand that true does not imply y is greater than x.
Okay.
But what was the point then?
What was the point? Good. Anybody want to try? What's the point? You mean what's the point of proving this, or?
Like, what was the point of that statement?
Of that statement to say true implies y larger than x.
Yeah, what was the point of disproving?
Oh, well, because if you, okay, remember why we do, step number 1, we understand that given this particular, let me use a different color. Given this particular strategy of implementation, we want to establish this particular x larger than y, right? That's what we want to do. In order to know what is the weakest precondition for doing that, we do step number 1. What we get eventually is y larger than x. That means in order for the program to be correct, the precondition itself must be no weaker than this particular weakest precondition, right? Let me just show you one more diagram, okay? It's from last time.
So we're saying true is weaker.
True is actually, no, true is actually strong, yes, it's weaker than that, you're right. Yeah, it should be no weaker than that, yes. Yeah, let me just remind you one more diagram, okay? Sorry, it's a little bit. Okay, remember that's what we had over here. In general, this is a diagram we want to be also keep in mind, right? So given this particular post-condition R over here, given some implementation strategy, we want to make sure whatever weakest precondition we calculate, the actual precondition, the green one, is no weaker than that. But in this case, it is.
Okay.
Because true is weaker than anything. Okay, good. Guys, it's really important to get a big picture because you may not get the same problem in the exam, right? Questions? Yes.
Professor, how does the step 2 establish the post-condition in the actual question?
How does, say that again, what?
So step 2, we just compared the weak precondition with the implication of the precondition, right?
Yeah, so, okay, good question. So when in step number 2, if you're basically, okay, let me just annotate this. In step number 2, you know that the y larger than x is the WP we just calculated, right? And true is the actual precondition, which is Q, that we keep talking about. And remember what WP here really is. WP is the one for S, the implementation to establish R. So that one there already accommodates R somehow, right? Since we have already done a simplification in the step 1, okay? So try to get a big picture very clear from this complete example, right? Make sure you know what you're doing, okay? The remaining part will be very mechanical, okay? Guys, any questions? Yeah?
clarify one thing. So basically here we're trying to check if the program is programmatically correct.
Yes. Basically, when you ask to see if this program is correct, you're basically asking the following. Given that the precondition is simply just true, which means any input is okay, and then we impose this, we execute this particular implementation, are we always guaranteed to establish this post-condition here? So now, based on our reasoning, the answer is no. Because the weakest precondition, logically speaking, it should be y larger than x. You're given something that's weaker. Okay? Yeah.
Are you going to be looking for the work? You want
If I give you something, that's kind of what I would expect from you. Yeah.
We can't just pop out y is greater than x.
You will get some partial credits. Yeah, you definitely get some partial credits. But I would say try to show us, exactly how you understood the reasoning. But I would say, for example, if you simply say, you can see over here, try to be very complete for you. But if you got, for example, WP for assignments, WP for assignments, WP for assignment, if you do all these three in one go, but I would say it's kind of risky to do so if you replace the wrong one. But I would say try to be very conventional here, right? Yeah. I wouldn't give you something that's terribly complicated. It's not reasonable, right? I'll give you something similar to this, maybe just slightly more complicated. Okay, slightly. How slightly it is, I'm not too sure yet. I can tell you most likely I'll give you something about loops, most likely. That's why we're going to talk about loops. Okay? I'll give you exercise and then I'll give you a solution for that particular exercise and you can study that. Okay? All right. All right, any more questions for me before I move on? Yes. Okay, let me say let me just write down exactly what you just said. You're saying that on the left-hand side, what do you get? Greater than 4, okay, and then? Then 3, okay. I would say in simple cases like this, you can simply say yes, it is obvious. But don't really try to say everything is obvious, right? But I'll say this one, yes. It is obvious that x larger than 4 implies x larger than 3. I would say this is a very simple case. That's okay. Yeah. Yeah. I would say maybe, for example, if I were to give you a question like this, maybe the main, most of the mark would be coming from step number 1. I want to see how you calculate WP. Usually step number 2, maybe only a very minor part. Yeah. No. You don't have to prove very formally. Yeah. Okay. Okay, guys. Any more questions? Yep. Will I give you example? You know what? We'll see example later. Okay. Yeah. Okay. Now let's go to loops. Okay. That's exactly what I just illustrated to you. And let's now go for loops. Okay, you learned about loop invariance in some of you who are studying 3101, but I'll try to maybe go from a different angle, right? Especially I'll show you how you can see loop invariance at runtime. That's actually more interesting to help you understand what loop invariance and loop variance is. So there are two concepts over here. Okay, so you pretty much know what a loop is. It's basically just having some progression every iteration. Okay. Okay, so now we can, the example we're going to use is to see how to find the maximum from an array. Okay? And usually loops are very hard to get right. I don't need to show you that. From experience, loop is very easy to get wrong. For example, infinite loops. I remember some of you yesterday in the lab test got infinite loops. That's why you couldn't launch the ES test. I was kind enough to tell you got infinite loops. Anyway. Be careful when you got infinite loop. Hopefully, after showing you the proof strategy, you will be able to see, right, why your loop might be infinite. Okay, infinite loop, you don't have a termination, or maybe somehow the loop counter was not set properly. Okay, or maybe just borderline cases. That's usually the one you will get wrong. Okay, and also not establishing the desired condition, which means you did something maybe that makes sense, but it doesn't really establish the post condition you desire. Okay, but that's something we'll go over by one example. Okay, if you go to OOSC2, again, one of the, which page is that? Okay, let me see which page. If you go to page 381 for the textbook, it's free. You can definitely get access to it. The point that they're trying to illustrate for that particular page is, so these are 4 possible algorithms for implementing binary search that has been published in the research community, but all of them are wrong. Okay, but the point is, it's really difficult to get binary search right. I can even prove that today. If I say, let's now have a quiz, and say, everybody, now write down in Java or Eiffel, whatever language you like, binary search. And then I'll take it in maybe 15 minutes. And then I guess, even myself, maybe 90% of us will get something wrong with binary search, especially for the boundary cases. Okay? But the point is, we do want to at least get a sense about what it means for a loop to be correct. And when we talk about correctness, there are two parts. One is about termination, and the other one is about partial correctness, which means assuming that it's going to terminate, is it going to establish the desired postcondition, right? So these are the two concerns. Okay. Okay, let's study a little bit of syntax quickly. Okay. For those of you who are still not very comfortable with the Eiffel loop syntax, okay. So this is kind of like a correspondence, okay, for between Eiffel and Java. Hopefully you've already seen that, but let's just see that very quickly, okay? And then we'll add two new keywords to our syntax. Okay, first of all, you can see that basically the only thing you have to get used to is when you say until B, that means as soon as B is satisfied, we're going to exit from the loop. On the other hand, if you want to translate this into Java, for example, using a while loop, you're going to say as long as B is not the case, I'm going to stay in the loop, right? Logically speaking, they're just negation of each other. Other than that, the body of the loop will be just corresponding to each other, and also what you do beforehand to do something to prepare for the loop will also be something similar, right? The concept is very similar. The only thing you have to be very careful about is think about the Boolean condition we have in Eiffel loop. It's more like an exit condition, okay? Exit. It's called so-called exit condition. On the other hand, the not be over here is the stay condition. Okay? Are we okay with this? If you're okay with this, let's learn about more. So now, if I want to make sure any particular loop I'm given is actually correct, at the moment, I only got implementation stuff. I have no contracts. If you want to prove a particular feature is correct, you need a precondition, you need a postcondition. But over here, we don't have any contracts, basically, for the loop. We simply say, well, if you start with this precondition over here, you start with this particular postcondition, we're asking the following question. When the loop actually terminates, is it going to establish R? If you only got a syntax like this, it is not sufficient enough for you to figure out the answer. Okay? We need something additional to help you with the proof. So what we're going to introduce to you is one thing is called loop invariance, which some of you may have heard already. Have you heard about loop variance? No? Maybe yes. Okay, but we'll cover that, but don't worry. Okay? So let's see. So we're going to cover two new keywords. Let's get used to the keyword, okay? So we still got a from. So now the new keyword is called invariant. Well, we learned about this new invariant already, but so far we only put it at the class level. For each loop, you can also have an invariant, which means this condition should always be true. Otherwise, your loop is considered as incorrect. And it's going to be some Boolean expression. Well, we'll give you example. Until B is true, we're going to exit. And then we have a loop body. And then, which means as long as the invariant has been true, and also the exit condition has not been true yet, we're going to execute the body for as many times as we like, as it will require. And now, finally, this is a new keyword here, definitely new. Okay, it's a variance. Variant is just another condition. However, the condition itself is not exactly Boolean. It's actually an integer expression. Intuitively, loop variance is a way for you to measure if your loop is going to terminate. And loop invariant is going to be used to measure if your loop, upon termination, is going to establish the desired postcondition. So they got two different purposes. Let's get a little bit more intuition about variance, and then I'll show you an example. The variance over here is going to be some integer expression, which will depend on maybe the value of the loop counter, let's say. Somehow you want to make sure the loop variant expression will change its value after each iteration. And then every time when you want to go from one iteration to another, the value of the variance must be strictly decreasing. And then eventually it will get very close to 0. Once it gets to 0, that means it's time to terminate. Otherwise, you got some issue with your loop. Okay, that's how we measure the termination of loop intuitively. But let's see a very simple example, just to make sure you understand the overall workflow. Okay, let's look at that. So that's the syntax over here. Okay, let's again to mention something you should really pay attention to, and then we'll see the how it is checked at runtime. So we have invariance over here. It's a Boolean expression, like a precondition or postcondition. And also we got variance over here. It's simply just an integer expression. For example, let's say if you got your loop counter called I, it can be 10 minus I, for example, right? Something like that. And then we also got our state condition. We got our body of the loop, and also we got our initialization steps. Okay, so we got these 1, 2, 3, 4, 5. These 5 components of the loop. So now, how is this checked at the runtime? I guess that's something you haven't really learned at 3101. Okay, that's something that we can complement your understanding. Okay, let's see. So that the flow chart over there, the control flow diagram there. Let's just go from the beginning. You know what? In order to even make the point even better, let me use different color of highlights to show you. Let's say we have over here the initially we're going to execute this part only once. That means we're going to execute this. After which we're going to reach a state. The state I put a kind of like a dotted line. Simply means the state may or may not be safe for the loop to start just yet. We don't know. How do we know the state is safe for the loop to start? Check the invariance. Okay, so now you can see that over here, invariance will actually be checked even before the body of the loop is executed for the very first time. Okay, so now this is the invariant expression here. We say that only if the invariant is satisfied, and we are going to check something more to see if we should go into the loop. If the invariant is simply not satisfied, in that case, it's going to be a loop invariant violation. I'll show you a concrete example. Okay, just get some abstract idea first. Okay, so far so good. So first of all, let me say one more thing. First of all, after you initialize whatever you like, you're going to check to see if the invariant is satisfied or not. If it is, you go ahead and check to see if you should go into the loop for the very first time. Questions?
What's the difference between variant and invariant?
Briefly speaking, invariant is a Boolean condition. And variance is an integer expression. Okay, good. So now let's say if the invariant is satisfied, and then that means it's green states for us to start. However, we want to know whether or not it's already time to exit. Okay, so what I will highlight is over here. You can see as soon as B is satisfied, we have to exit from the loop, right? So it's definitely possible that we don't even execute the body of the loop for the very first time. It's definitely possible. Okay, so that means if it is not the case that the exit condition is satisfied, we can now start executing the body of the loop for the very first time. And then we simply go ahead and execute. So we go into the body, and then we just execute for the very first time. Okay? At the end of the execution, let's say at the end of the first iteration, what we will do is we're going to check to see whether or not the termination concern has been satisfied. Okay? What we will do is like this. Okay? Let me use maybe pink. Okay, you can see the variant expression is V over here. So after at the end of the first iteration, we try to see if the V is, I should really put it this way. If V is larger than or equal to 0, okay, it has to be non-negative. If it is still non-negative, that means we are allowed to go on to execute the next iteration. If it is already negative, that means there's something wrong. Okay? Okay, you will see that if in the case where the variant is already negative, that means we got some loop variance violation. Okay, so you can see upon the termination of the body of the loop, if the variant is still non-negative, and it's not a safe state yet for us to really go on for the second iteration, what we should do is we go on to check to see if the invariant is satisfied. If it is not, we might have another loop invariant violation. Otherwise, we can go on to see if it is now time to exit. If it's not time to exit, we'll go on to for the second iteration, and so on. Guys, are we okay with this diagram here? Okay. Okay, stare at that for a moment, and then let me know if you got any questions before we see one concrete example. Yes?
Oh, this is a question about loop variant.
Loop variant, okay.
Comparing it with 0?
I would say, as far as, well, since we are only learning the introduction, I would say think about, you try to specify the loop variance, which is integer, such that it's going to start with some value, and then immediately after the last iteration, it's going to be decreased to exactly 0.
And with the set the v.
We set a v. And we will see example in just a moment. Yeah. Yeah. How you set a variance, we do have a standard way of doing it, just for the introduction, right? Yeah. Has any questions about this diagram here? Okay, let's keep the same diagram, but I'll give you a concrete example for each part. Okay, let's trace that together. And then after that, we'll do a slightly more complicated example. Okay, it's a very, very easy program. Basically, it simply just go from, let me just, again, let me be, okay. What I will do is, you can see that over here, we have some loop counter I, and then initially, we simply say initialize I to be 1. Okay, and then, what about the invariance? Invariance green, so I'll put green here. And then the invariant is simply saying that from the very first, at the end of the first iteration until at the end of the last iteration, I should always be between 1 and 6, always. Okay? Now, what about exit condition? Let me remind myself the color. And then orange. And then, as soon as I is strictly larger than 5, which means as soon as I becomes 6, we're going to exit from the loop, okay, as soon as it becomes. And then the body of the loop is going to be blue, so I will put blue here. Okay, we're going to do two things. Of course, we got to make sure we increment the counter, it's common practice. And also, we're going to print out some string just to say iteration and then ida out. Iteration 1, iteration 2, etc. And then the variance, which I should put in pink. The variance is going to be some integer expression, 6 minus I. Okay? Stare at that for a moment. Okay? So that's a very concrete example for you, as easy as I can do. What we're going to do is, we'll try to trace this program altogether quickly. Before we try to trace, based on your knowledge from many semesters ago, so now, what should be the output? It's going to be io.putString, right? Iteration ida out, right? How many lines should it be output? Okay, we definitely get iteration 1, agree? Will we get iteration 2? Iteration 3? Iteration 4? Iteration 5? Iteration 6? No, right? Okay, good. Because as soon as I get to 6, you satisfy the exit condition I larger than 5, you don't get a chance. Okay, let's keep that in mind. Okay. Now, let's have a look to see how this can be checked. Let's now try initially, okay, after, let me be a little bit more abstract over here. After the inits, we know that I is simply just 1. Okay? And then we try to make sure if I over here, which is I should be less than or equal to 1 and, larger than or equal to between 1 and 6. Is that the case initially? Well, 1 over here satisfies this predicate over here, right? Agree? So that's okay. So we're going to go into a safe state. We're going to check further. The B over here is simply I larger than 5, right? Not the case, I larger than 5 is I less than or equal to 5. Agree? Okay, now I, which is 1, is less than or equal to 5. That means we can go ahead and execute the body of the loop for the first time. And the body of the loop is going to say, first of all, iteration 1, okay, and then it's going to increment I from 1 to 2. Agree? So that means after this, we're going to go into, and then I will just be 2 at this point, at the end. And now at the end of the loop, what we have to do is, we have to make sure the variant is still satisfied. And the variant itself, over here, is 6 minus I. 6 minus I. So in this case, 6 minus 2 would be 4. 4 larger than or equal to 0, that's okay. So far so good. Okay? So we go back to the beginning of the loop, in which case I has become just 2, right? Are we okay so far? That's the very first iteration. Okay? I'm going to skip the iteration 2, 3, 4. Let's go to iteration 5 directly, okay? Yeah. Otherwise, it would be too boring. Okay, let's assume that we're going to get iteration 1. Let me just put here. Iteration 1, 2, 3, 4. Okay? Let's say after iteration 4, at the end of iteration 4, I would be incremented to just 5, right? After I has been incremented to 5, 6 minus I will give me 1, right? Still larger than or equal to 0. That's okay. Okay? And then, so that means I is going to be 5. Now, let's see if we can go to the 6th iteration. Okay? So now, I think we can, but let's try. When I is equal to 5, what we're going to do is, well, we'll use a different color. Let's say red. I is equal to 5, and now I is still within this range, between 1 and 6, so we are fine. And then, we're going to see I is less than or equal to 5, so we'll go in there, seems to be for the very final time, right? I is equal to 5. And now we go in here, and then the body of the loop is going to say iteration 5, right? And now, remember, it's going to increment the value, so I will be incremented to 6. Okay, that's the last, seems to be the last iteration. Now, I is equal to 6. 6 minus 6, 0. So larger than or equal to 0. So you should not decrement anymore. Okay, so 6 will be equal to 0, so we are fine. And now I would just be 6. And now, it seems that we should exit from the loop, because 6 less than or equal to 5 will give me false. That means I should really exit from the loop. However, one thing you should really keep in mind, upon the termination of the loop, after the last iteration, the invariant should still be satisfied. It should. Okay? Invariant should always be satisfied. Okay? Either before or after either before the first iteration or after the final iteration. And now, after the final iteration, I is simply 6. 6 is still within 1 and 6, right? So that means we're okay. So after some runtime test over here, it seems like this particular loop is okay. Of course, we don't have any post condition just yet. Okay? Guys, any question about this? I hope the idea is clear. Yes? If the invariant, you know what? If the invariant is too weak, what is the weakest invariant you can put here? The weakest. True. If you put true here, it's as if you have no invariance. And that's pretty much what you have done so far. So you will never catch any loop invariant violation for you. But that's not like a false positive, right? Because you simply have nothing that's meaningful for you to check. Yeah. So, well, that's something we'll talk about. Yeah. So that's the correct version. To strengthen your understanding, I would like to modify stuff a little bit. Let's see how we can trigger some invariance, some violation. Okay. Hopefully that will be helping as well. Okay. Next one. The same code. Let's see how we can trigger a invariance violation. Okay. Invariant. Loop invariant violation. You can definitely give it a try. Okay. It's very easy to put this code on Eiffel. Okay. Now, how can we trigger an invariant violation? What about I simply change from 6 to 5? Think about it. Are we going to get a loop invariant violation? When?
Before the final iteration.
Final iteration. Is it? Okay, how about this? We got 5 iterations in total, right? Is it after the 5th iteration or before the 5th iteration? After the 5th, right? Because we know that in the 5th iteration, I would just be, okay, in the 5th iteration, I would just be 5 to start with. And then after the increments, we're going to get I would be exactly just 6, right? So when we go back and check, we're going to see that it's not within this particular boundary. You're going to get looping variant violation. Okay? Now, let's see another one. Okay, how about this? Can you give me another invariance? I want to have a looping variance violation much earlier. Can I have a looping variant violation even before the first iteration? Give me one predicate. Give me one Boolean expression for. Oh yeah, of course. That's one way to do it. Yeah, but you're changing the initialization. But what about changing the looping variant itself? Yeah, exactly, right? Okay, very good. Okay, just wanted to make sure. Yeah, so what Raymond suggested was, if I simply change this to be 6, for example, right? We're going to get the looping variant violation right away, right? Even before the first iteration. That's good. I like that. On the other hand, we can also, let's say, get rid of this. I simply say I is less than 1. But if you actually got violation like this, that means you got some problem, right? You actually just initialize your loop so that it will fail. Okay, but I'm just trying to show you. Okay? All right. Now, let's try to see how we can get a, let me just undo. Okay, that's about a looping variant violation. How can we get a loop variance violation? Yeah, of course, if I want to get a loop variant violation, there are 2 ways you can get it. Either you can try to just modify the variant expression itself, which is what I'm going to show you. Okay, you can also try other. You can, for example, you can simply say loop over there rather than oh, actually, that's fine. This would be better. Let's forget about what I just said. So now, how can we, let's say 5 minus I. Okay, so rather than 6 over here, let's say 5 minus I. Okay, now, when will we get a loop variance violation? Yeah, because after the 4th iteration, I becomes 5, right? Now, that's okay. 5 minus 5 is still fine. But after the 5th iteration, I will be incremented from 5 to 6. Now, 5 minus 6 will be minus 1, which is not larger than or equal to 0. So this will be false. So that means we go to this branch. Okay? Do you think about why this will be a loop variant violation? Okay? Is there another way to have a loop variance right away? Not really right away, because variant, the very first check for the variance is only at the end of the first iteration, as you can see from the chart, right? How do I get a loop variant violation right after the first iteration? Yeah, go ahead. No, actually, I want the loop variance violation right after the first iteration. Yeah, so I want to make sure after executing this part of the code for the very first time, I want a loop variance violation. How can I do that? Well, that's one way, right? Exactly. So now let me just say that to everybody, and then I'll answer your question. So what you just suggested was, let's say I is still initially 1, and then I'll say, well, I is simply just I plus 6. In that case, you will simply get 7. And then variance will be 5, either 5 or 6 minus 6, and then you will just get a negative number, right? Good. Yeah, questions? Go ahead.
We're doing I becomes equal to I plus 2. Okay, instead of I becomes equal to I plus 1.
Uh-huh.
So the first, like, 3 times it would be okay.
Yeah.
And then it would fail.
And then you will fail because you will get to the negative. Yeah. So let me just mention that, and guys, you can think about it as well. It's just another example. So that means for as far as the introduction for this course is concerned, you would want to make sure you design your variance such that it just reaches 0 right when you actually have to exit from the loop. Okay. So now let me just mention what you just said in a clear way. Okay. So what you just suggested was, you're suggesting maybe I is assigned to I plus 2. Okay. Let's see exactly how this is going to happen. Think about the I value. And also, let's say we still got 6 minus I. Okay, now, okay, let's say before the first iteration, I is simply just 1 initially, right? Now, after the first iteration, let's say I put iteration over here. After the first iteration, I will be incremented to 2. In which case, 6 minus I would be 4. You're right. Sorry about that. You're right. I'm still thinking about plus 1. Good. Good. You decided the error. That's good. So now after the first iteration, I will be incremented by 2. So that'll be 3. So 6 minus 3 will be 3. That is fine. So 3 is still larger than or equal to 0. That's good. Now what about after the second iteration? We'll be incremented from 3 to 5, right? 6 minus 5 will give us 1. 1 is still larger than or equal to 0. We're still okay. Okay? Now, after the third iteration, we got 7. 6 minus 7, oops, right? Minus 1 larger than or equal to 0 will be false. That means we'll go to loop variance violation.
What if that's what you want to do?
In that case, well, what they would check at the runtime is to say if, well, at the runtime somehow they simply make sure your variant never gets to minus 1. Yeah, so if you only meant to run, let's say only 3 iterations, you may just want to say 3 minus I, right? Or something like that.
Okay.
Yeah. We're going to see, before I take any further questions, the more complicated example we're going to see is you may want to run a loop over an array to find the maximum value. Okay? And now, basically, we're doing a linear search. When you do a linear search, the number of iterations will just correspond to how large the array is. So you will see some standard way of specifying the variance. We wouldn't go to a very complicated example for this course. It's only to give you some flavor about what what program verification can be like. Okay? Questions? Yeah. Oh, you mean put a negative number right away? You're saying that. Sorry, are you suggesting to change the variance, or you mean to change this rather than 6 minus I, simply put minus 2? I never tried before. I suppose it will compile, but it will fail after the first iteration. Yeah, that's what my guess is. Yeah, but that's interesting about what would you do there, right? Yeah.
Professor, so you have two kind of
Violation.
Variance, invariant, and the variant to predict your loop from wrongful iterations, right? So how do you use those to kind of look forward to get rid of infinite loops?
Oh.
Those two things wouldn't protect you.
So to really prevent yourself from infinite loop, think about what infinite loop really means. That means you never get to, you just keep executing the body of the loop, right? So what the loop variant will make sure is, you want to make sure 2 things for the loop variance. Loop variant, okay, yeah. Oops. So what you want to make sure is, for this loop variance over here, okay, let me just clear this part here, and then write something for you over here. So for loop variance over here, this is to ensure termination. On the other hand, the invariance over here is to ensure correctness. Okay, it's a separation of concern. So again, let me just repeat the intuition you should have. How does the loop variance ensure termination in the following way? There are 2 aspects for the variance. Number 1, you want to make sure the variance value gets strictly decremented after each iteration, from 6 to 5, 5 to 4, 3 to 2, and 2 to 1. It doesn't matter how much you actually decrement it. It can be decremented by 2, decremented by 1, doesn't matter. As long as its value is strictly decreasing between iteration, number 1. Number 2, you want to make sure the value for the variance expression is always non-negative, right? Basically, thinking this way, intuitively, if this is the level for 0, you may start your variance with some level over here. That's the initial, after the very first iteration, right? You want to make sure you always try to decrease, doesn't matter how little or how large it is. Eventually, you will make sure it never goes below 0, right? That's kind of, so, and now, since every step over here is strictly larger than 0, that means the number of levels you had to decrease will be finite. That means it's gonna be an infinite loop. That's kind of the intuition.
The thing is, it's an infinite loop when you don't have the incrementer, the rising compliance.
Yeah, so now, good. So let's say this. We know very well. Of course, we'll get to the proof rule a little bit later, okay? Let's say this. Hypothetically, if I simply just get rid of this part over here, We know very well, I don't need to show it to you, right? If I get rid of I, it's assigned to I plus 1. What does that mean? That means the loop variance value over there will always be 5, right? Because I stays at 1. So that means the variance doesn't really strictly decreasing. And that's going to give you some violation at the runtime. Yeah.
I increase. So if I start set like array.count,
Yep.
and we keep decrementing,
Yep.
what would the variance be?
We will see that. It's a very good question. You're asking if we are iterating through an array of size 10, for example. We are expecting 10 iterations exactly. How can we specify the variance so that it will just decrease just down to 0? But we'll see that. Okay? Yeah.
Oh, Professor, so if we remove the I plus 1 over there, then
Yeah.
the variance always fine, right?
Invariance is okay, but remember invariant is a different concern. The variance. The variant is
Always going to be fine.
exactly.
And then we said that we're going to get some variance.
Yeah, I think for this one, yes. Because since you got a variant expression there, Eiffel runtime will make sure every time when you go from one iteration to the other, it will make sure the value, the old value for the variant, which is 6, should be strictly larger than the new value for the variant. In this case, it can be 5, right? Yeah, we'll see more example like that. Again, 2 things about the variance. It must be always non-negative, and also it must be always strictly decreasing between iterations. Strictly. That's why maybe you can think about this level over here, right? You can think about this is the level for the variance value. It must be decreasing just strictly larger than 0. And we know that the value between 0 and some concrete value for V will just be finite. So the number of iteration will also be finite. Yeah. So we're using the variant to measure roughly how many times you're going to execute a loop. Okay? Okay, good. Guys, any more questions about this? Okay, next. One more slide to show you. So this is a different way of thinking about a loop. Okay, we are more thinking about predicates. Okay, basically what we're doing, I will just brief you very quickly. You can think about this is kind of the starting states before we get to the beginning of the loop, which is the front part, right? So we're going to execute the initialization. After the initialization, we should go to a state that's within this particular set. And that set is exactly captured by the invariance, which means whatever state you calculate within the loop, you must be within the invariance, which means satisfy the invariance. Okay? And then you may execute the body of the loop for as many times as you like. Okay? But it must be within the region for the invariance. Okay? Now, we have another condition over here, which is the exit condition. As soon as you reach a state that's within the exit condition, which means the exit condition is true, in that case, you have to exit from the loop. As soon as you exit from the loop, you want to make sure this is the most important part. The state over here is also within another set, which is the post condition. Okay? That's just another view for the loop. Okay? What we just talked about is more like a mechanical view, how you check it at the runtime. This is more high level. We also bring post condition into play. Okay, any questions about this? Okay, let's see another example. Okay, so now that's about the counter. Okay, so let me just say one more thing. How do we specify the looping variance? Looping variance is just going to be a Boolean expression. I would say typically, if you're trying to go through an array, let me just use a slide to show you. Let's use this, let me just use another one. Let's use one example. Let's say let's say over here, let's only talk about the looping variance. Let's say we got a local variable, so we have I, loop counter, and also we're trying to calculate the sum of the array. Integer. Okay? And then we want to say from I is assigned to, also we got, let's assume we got an array. Okay? An array that's going to be of size, let's say 4. Okay? And then I is assigned to a dot lower, and the sum is simply just going to be 0. Okay? Just that. And then we have an invariance over here, which I will show you how we can derive that in just a moment. Okay, something here, I'll put a question mark. And then we have loop over here. And loop is very easy, which is the sum is assigned to sum plus 8 at position I. And then make sure you increment the loop. Let's not worry about the variance, okay? Okay, let's say this is about some feature. Let's say eventually we have an ensure. Okay, ensure. Okay, ensure. Let me just try to be a little bit more precise for you, so you can also reproduce this on Eiffel. Okay. Let me say I simply want to calculate the sum, and that is going to take an array A, array of, sorry, that's a little bit bad. That's simply going to be an array of integer, and then it's going to return the sum, which is just another integer. Okay, so I'm just going to get rid of the sum over here. Instead, I'm going to put result. Okay, I'm just get over here. I can say result is simply assigned to 0, and now what would be the post condition? I'll specify the post condition for you. Okay, and then ensure for this particular query over here, I'll put it in blue. Let's just use sigma, mathematical. Okay, I can say result is simply just assigned to sigma. Okay, and then I can say I is assigned to a dot lower until a dot upper, and then a I. Are you okay with this expression here? Sigma. All right, that's the post condition, which means eventually the value for the result must be the summation from the element at a dot lower until the element at a dot upper. Okay, that's the post condition. So now the question is, how can we actually specify the post condition? Oh, sorry, not the loop invariance. That's the question. Let me give you a little bit hints over here. Conceptually, think about it this way. You want to somehow to say the result, in this case, is somehow the result is going to be accumulated. You want to say what's the, how do we define the correctness of the accumulated value so far? Okay. So now thinking this way over here, let's say, let's be very concrete. Let's say we got 2, we got 3, we got 4, we got 5, right? And now I initially is simply just 1. Just 1, right? We want to make sure if we're thinking this way. You can think about after the first iteration, the result must be covering this part of the array and get a sum. After the second iteration, you should really get a sum for these two elements. After the third part, after the third iteration, you should really cover this part. After the fourth part, it should be this. As soon as we exit, you should cover the entire array. That's the intuition, right? So loop invariance is really to say, based on what we have discovered so far in the array, which can be partial, how do we define that partial result to be correct? And typically, the loop invariant will be very similar to the post condition. Very similar. Okay? Now, let's figure this out together. Okay. You want to ask a question or you want to suggest? You definitely need until. Yes, I forgot. Absolutely. Until, and then I greater than a dot upper. So termination is not an issue, so don't worry. Good. Okay. Now, how do we specify the loop invariance? I can give you a little bit hints. It's going to be basically look just almost like the post condition. Okay. You can definitely refer to the result. Okay. Is equal to sigma I. Let's say since I is already, you know what? I is not a good choice because I is a loop counter. I will change from the post condition rather than I will say J. That'll be better. Okay, just J. And then over here, I also say J. So I have no clashing with the loop counter. So now I would say J is equal to something until something, and then A, J. I'm almost done with the looping variance, but now I just want to know which part of the array I'm talking about based on what I have calculated so far. Eventually, I should really cover the entire array upon termination. But what about before the termination? Okay, I like that, but we'll see if that's right or wrong. We'll see. Okay, I like that. Good. You're suggesting j will be eta lower until j will be 1. Is that what? Oh, I. Sorry. Of course. Are you sure? Okay. So now what I would do is, you know what? Let me just be very precise to you. Let me just redraw this array. Actually, this part is really important. We can save some time when I talk about a more complicated example. Okay, let me just put this back. 2, 3, 4, 5. Okay, and now result. Let's keep in track of the result. Now let's be careful here. Okay. Now let me. So for the very first line, I is gonna be a dot lower. Okay. Let's say a dot lower. Let's say we have indices 1, 2, 3, 4. Okay. So I will be a dot lower. That means I is simply just 1. Okay. After this step. And what about after the second step? Result would just be 0. Would just be 0, right? Now, according to what we learned from previously, we know that as soon as after we do the initialization, we have to check invariance right away. Agree? So now what's going to happen? Let's try. It's really important. So now what's going to happen is I is already 1, right? That means what we get is result is equal to sigma j is assigned to a dot lower is simply just 1 until I is also 1. Agree? And now a j. Now, can you help me simplify this part of the sigma? What would that be? 2, right? What's the result? 0 equal to 2. You got a looping variant violation. It's a very common mistake. Okay? Because we are only expecting 2 after the end of the first iteration, not before that. Any suggestion? Oh, you got a question? Yeah, before I hear your suggestion.
What happens if you initially set result to be the first index?
You may do that, but let's say we stick with this. Yeah, the suggestion was, what about we simply set the result initially to be A1? That's one way to fix it. Sure, I might give you that in the exam, but let's stick with this. Okay. Any suggestion to fix? Okay. Now, however, do you think this makes sense though? Now, the fix you're suggesting was, what about we simply say over here, I minus 1. Okay. No. Minus 1. So what does that mean? If we say I minus 1, what's going to happen is now rather than 1 over here, it's going to be 0. So that means j is going to be from 1 to 0. That means we are basically talking about interval like this, 1 and 0, right? In that case, it's simply empty interval, which means nothing to calculate, which means it's 0. Okay, good. This will give us 0, and 0 is exactly equal to 0. Guys, are we okay with this? So what do we learn from this? What we learn from this is when we specify the looping variant on the big picture, it must be almost like the post condition, except that we are trying to play a little bit about what we have gone so far for the loop counter. However, if you simply specify like what you suggested, we simply just do I over here, it wouldn't be enough. It wouldn't be correct because only after the initialization will we have to already calculate the invariance, but that's too early, right? That's so that means we have to fix it, the upper bound over here. That means it has to be I minus 1. Guys, are we okay with this? It should be I rather than I minus 1. Oh, sorry, it should be I minus 1 rather than I, right? Wrong conclusion, but the reasoning was okay. So now the conclusion is the loop invariance will be exactly this one over here. I'll repeat once more. It will be result is equal to sigma j is a dot lower and then I minus 1 and aj. That's the loop invariance. Now let me go one step further. Okay, how how is this looping variant connected to the final post condition, right? Think about this. Let me say I will highlight the following. Let me highlight the looping variance over here. Okay, first of all, consider this looping variance over here in blue. At the same time, can you also look at the post condition in orange? How are they connected? I have a hint for you. The hint is exactly what Raymond reminded me about, the exit condition. Can you see the connection here? Aha, okay. In that case, I minus 1 would be exact. Okay, very good. Okay, very good. So let me repeat. We know that the pink one over here tells us when should we exit from the loop. We know that as soon as we exit from the loop, that means I is strictly larger than A dot upper. Or we can say I is simply just equal to A dot upper plus 1. Agree? That's like from 5 to 6, right? So now when I becomes A dot upper plus 1, that means we can replace over here by A dot upper plus 1. So what do we get eventually? A dot upper. Isn't that exactly identical to the post condition? Okay, that's kind of the insight into this particular pattern, which means we try to make our looping variance very similar to the post condition, so easier for us to judge the correctness. At the same time, at the runtime, after each iteration, you can also check to see if that invariant is satisfied throughout. Okay, guys, how much time do I have? 10 minutes? Really? Oh, okay. Do I have 1 minute, maybe? Okay, 1 minute. Okay. Okay. I think I do have one more example to show you, but I think we have learned enough. Okay. How about this? For today is Thursday, right? Okay, yeah. So for next Tuesday, last lecture. So make sure you come. I'll also put a new Moodle announcement. I'm going to talk about the exam after certain materials, but we definitely finish up the materials. I'll try to see if there's anything new I can cover also for your knowledge. Okay, I'll see you on Tuesday.